Hi. So today I will be discussing the rest of the topic under our Thyristor. We will review the SCR, then we will proceed to Triac, Diac, UJT, PUT, and Opto-Thyristor. MOSFET if we can. Okay, so let's proceed. As a review, we have silicon control rectifier. The SCR has its roots in the 4-layer diode. By adding a gate connection, the SCR could be triggered into conduction. The SCR is the most widely used thyristor. It can switch a very large current on and off. The SCR can be turned on by exceeding the forward breakover voltage or the gate current. The gate current controls the amount of forward breakover voltage required for turning it on. The SCR is far more useful than a 4-layer diode or the Shockley because the gate triggering, this one, is easier than breakover triggering. As you can remember from the Shockley, by the gate voltage, as you can see here, we can switch on SCR easily rather than waiting for it to reach the breakover voltage applied at the anode to cathode terminal. So, like the 4-layer diode, the SCR will conduct as long as forward current exceeds the holding current. There are two ways to drop the SCR out of conduction, and that is by anode current interruption, or this one, or force commutation. The anode current can be interrupted by breaking the anode part, this one, providing the path around the SCR or dropping the anode voltage to a point that IA is less than IH. Our typical turn off of SCR is the anode current interruption, or we lower the supply voltage across the anode to cathode. Anode to current can be interrupted by breaking the anode part, anode current path, providing a path around the SCR, or dropping the anode voltage where making IA is less than IH, while force commutation uses an external circuit to momentarily force the current in the opposite direction to forward conduction. The basic circuit consists of a switch and a capacitor. This one. While the SCR is conducting, the switch is open and CC is charging to the supply voltage through RC, this one. To turn off the SCR, the switch is closed, placing the capacitor across the SCR, forcing the current through it opposite the forward current. SCRs are commonly used in the AC circuit, which forces SCR out of conduction when the AC reverses. By using this force commutation, as you can remember, SCR is a unidirectional device. Three important SCR specifications are the forward breakover voltage, or the supply across the anode to cathode, the holding current, which we need to exceed for it to be able to switch to conduction mode, and the gate triggering current, where we apply at the gate terminal to increase or to increase the time or trigger the SCR faster than the breakover voltage, the time it takes for the breakover voltage to switch on. So, SCR applications, we have on and off control of current. The figure shown an SCR circuit that permits current, this one. So this means this is gate triggering because you apply a switch here. This is the gate triggering. Now this is the breakover voltage. An SCR circuit that permits current to be switched to a load by a momentary closure of the switch and removed from the load by momentarily closure of the switch too. This one is the force commutation. No. Because force commutation needs a capacitor. Closure of switch 1 provides a pulse of current into the gate, thus triggering the SCR on. When the switch 2 is momentarily closed, the current is shunted through the SCR, thus reducing the anode current below the holding current. This turns off the SCR. So this seems like a forced commutation, but again, by closing this switch 2, the current flow will go to the less resistive path. That's why it will go across here, dividing IA into I going to the ground here and the I going to the SCR. That's why it momentarily decreases the current across the SCR. Determine the gate triggering current and the anode current when the switch 1 is momentarily closed in figure 1-16. So we have equation of IG, which is voltage triggered and voltage across the VGK. So what is the VGK? VGK is this one. Provided, usually 0.7, when you say 0.7, that is silicon. So gate triggering, meaning you have to do a KCL around voltage triggered 3 volts by applying KCL here. Okay? We can have by KCL at the gate, okay? So we have gate triggered VG equals IG times RG plus this one, the voltage across the SCR. So that will be plus Y plus, because this will be the flow of the current through VGA. The flow of the current through VGA here is negative positive. So this follows the negative and positive. So when you do the flow here, okay, that is plus because it follows the flow of the current. So that will be plus VGK, gate to current, to cathode, making it, by transposing that will be VG minus VGK equals IG, and since the unknown is IG, we just divide RG by IG to get the current across the gate, making it in this format: 3 volts minus 0.7 over 5.6K, resulting to 410 microampere. So so this is the IG. Okay, so the triggering current. What now is the holding current? The holding current is IH. So assume this part is 15 volts. Determine the anode current, the triggering current, the anode current. So how do we find the VAG? So again, by KCL at what? This one, downward, okay, IG. This one, A. So, by KCL at IA, this loop, this downward at anode to cathode, we will have VAK is equal to IA times RA plus VGK. Again, where that VGK come from? This one, across the SCR. Simplifying, that will be VAK minus, because we are going to transpose the VGK, minus VGK equals IA RA. Upon having that, transposing RA on the other side, we will have the equation for our IA. That's why we derive this equation. So that means we don't need to memorize this equation, because by applying KCL and KVL only, you can determine the equation. So we will have a anode to cathode current around 448 milliampere. So that is the equation here. A common application of SCRs is the control of AC power. For a lamp dimmer, electric heater, and electric motors, a half-wave variable resistance phase control circuit is shown here. RL represents the load, or the resistance of the load. R1 limits the current, and the potentiometer of R2 sets the trigger level of the SCR. As you can see here, we have a diode as our triggering element. By adjusting R2, the SCR can be made to trigger at any point of the positive cycle of the AC, performing between 0 to 90 degrees as shown in the figure. Again, by adjusting the R2 or the potentiometer, we can trigger the SCR faster than the VAK. Half-wave power control, this one. At 90 degrees, this will be the level. At the triggering point, this can be the level. So that's the reason why SCR is called a unidirectional device, because it cut off the negative half cycle. Another example, when there is a current or load current, the SCR is conducting and the voltage across it is ideally 0. When there is no load current, the voltage across SCR is the same as the applied current. The waveform show as this one. Again, we have a diode. That's why our triggering device for our SCR is this diode, making this half circuit a half wave. Remember, in electronics 1, we have a diode to represent the half wave, to cut the supply, AC supply, into half, into one direction only, or rather one polarity only. Backlighting of a power interruptions. This circuit shown will maintain the lighting by using a backup battery. There's the battery. This one. When there is an AC power failure, as long as the AC power is available, the battery charges through the diode 3. This one. And the R1. Okay? Then, when there is an interruption of AC power, the SCR conducts the current flow from the battery, keeps it illuminating. So meaning, if we have a supply here, the flow of the current is going. See the the flow going that way. The SCR will give here at the same time charging the battery. Now, if there will be an interruption of the AC, the flow of the current will be going up, following the direction of the supply, going up to the SCR, giving a continuous light at this one. We also have Sawtooth Generator. The SCR can be used in conjunction with the RC circuit to produce a repetitive sawtooth wave. The time constant is set by R1 and RC, and the voltage at which the SCR triggers on is determined by the variable voltage divider formed by R2 and R3. When the switch is closed, the capacitor begins charging and turns on the SCR. When the SCR turns on, the capacitor quickly discharges to it. The anode current then decreases below the holding current, causing the SCR to turn off. As soon as the SCR is off, the capacitor starts charging again, then the cycle is repeated. That's why it is Sawtooth Generator, this one. Okay? By adjusting the potentiometer, the frequency of the sawtooth waveform can be changed. So we have Triac. Basically, a Triac can be thought as two SCR connected in parallel and in opposite direction with a common gate terminal. By this time, we say that is parallel in opposite direction with a common gate terminal. As you can see in the figure, this acts as, it looks like a Triac with extra gate, but it is not. It is the combination of two SCR connected reverse parallel with the common gate. Unlike the SCR, the Triac can conduct current in either direction when it is triggered on, depending on the polarity of the voltage across A1, A2 terminals. That means, if we compare, if Shockley diode is to Diac, then SCR is to Triac. Meaning, to make a Shockley diode bidirectional, we have a Diac. And if you want SCR to conduct bidirectional, we need a Triac. Okay? As you can see, the graph is the same as the Triac. Only now we have symmetrical in terms of the positive and the negative. We also have a reverse triggering during the negative cycle. The construction is this one, NPN, A1, anode 1, and anode 2. So we don't have negative terminal. And we have a gate terminal here across again the P junction. Or I insert a clip of the Triac, okay? So the characteristic curve shown that the breakover potential decreases as the gate current decreases, just as with the SCR. When the voltage on the A1 terminal is positive with respect to A2, the gate current pulse will cause the left SCR to conduct. When the anode voltage are reversed, the gate current pulse will cause the other SCR or the right SCR to conduct. As with other thyristors, the Triac ceases to conduct when the anode current drops below the specific voltage or the holding current. The only way to turn off Triac is to reduce current to the sufficient low level. So, comparing Triac to the other thyristor, we cannot do the anode current triggering. We just need to reduce the level of the current. Application. Like the SCR, Triacs can also use to control average power to a load by the method of phase control. The Triac can be triggered such that the AC power is supplied to the load for a controlled portion of each upcycle. During the positive half cycle, the triac is off for a certain interval called the delay angle. They are cutting. And then it is on for the remaining portion. Okay? That is called the conduction angle. Similar action of force in the negative half cycle. So now in triac, we have what we call the conduction angle. One example of phase control using the triac is shown below. Diodes are used to provide trigger pulses to the gate of the triac. Diode D1 conducts during the positive half cycle and D2 during the negative half cycle. The value of R1 sets to the point at which the triac triggers. Example, I have redrawn this one in the, of course, our friendly software simulator, everycircuit.com. So as you can see here, the definition of triac is that it is two SCR connected reverse parallel with the common gate. So this means this is wrong because why? We need a common gate. So this is the first SCR. This is the second SCR. As you can see, they are reverse parallel because we have here a PNP and here NPN. When we go here, we have NPN and here on the side, the bottom is the PNP. So where is the gate? This one. Common. This one. Play. See. So this is the waveform of the triac. As you can see, it conducts, the green one is the supply, AC supply, and the purple is the load current here. Meaning, it is cut or reduced, but still, they are operating in both directions, positive and negative. What will happen if we remove the diac? We turn it into SCR. It will look like this one. Now, this is an SCR. As you can see, SCR conducts only in one direction. See the waveform, output waveform of the load? It is cut during the half cycle. So that is why we have. But why, ma'am, it is not broken down? Diba? We have a positive, we have AC supply and yet it is safe to use the SCR. Remember, we have diodes. Diodes connected to the gate. That means our triggering device are the diode. During the positive half cycle, the flow of the current, look at the arrow of this. The flow of the current is from here, going to the downward, going to the diode, then to the potentiometer, then the SCR. If that is a negative half cycle here, but since we are cutting that, there will just reduce to zero. Okay?